(28) CPS Geometry. Lines patterns in space. As we have already stated, in CPS geometry, the points are infinitely small, identical spheres, arranged in a CPS pattern, filling up the CPS space. Let us build on this concept, and let's introduce the next fundamental concept of the CPS geometry, namely the straight line. As done in the classical geometry, the straight line is defined in CPS geometry as the simplest possible pattern, determined by any two CPS points, belonging to the CPS space. Any straight line pattern, determined by two CPS points, can be extended indefinitely, in two opposite directions. Such an unlimited pattern is in fact a complete, straight line in CPS. One can observe that a straight line is a periodic repetition of the same pattern, in both directions, indefinitely. As a consequence, the straight line in CPS contains an infinite number of points. If the basic pattern is not extended indefinitely, then we have a line segment in CPS. The sources of the infinite number of points, belonging to a straight line, are based on two facts. 1. The initial pattern is extended indefinitely in both directions, and 2. The CPS points are infinitesimal spheres. A line segment in CPS geometry still contains an infinite number of points, due to the fact that the points, in CPS geometry, are infinitesimal spheres. Let us look next for patterns, in the distribution of lines, in the CPS geometry. As stated already, any point can be connected with any other point, to define a straight line. To simplify our setup, without giving up its generality, we will investigate all the lines that are defined by one fixed CPS point. We will do this by performing mental experiments with the purpose of finding the fascicule of lines, emanating from a given CPS point. We will investigate this in two ways. 1. First, we will consider layers of CPS points, surrounding the initial point, and expanding in every possible direction. We have already seen this arrangement of CPS points in the Cuboctahedron pattern. As we move farther and farther away from the central point, the layers always completely surround the initial CPS point, shown here in red. By following this approach, we are sure we do not miss any point in the CPS arrangement, and subsequently, we are not missing any CPS line. The numbers of CPS points, on each layer, are given by the terms of the following sequence: 1, 12, 42, 92, 162, 252, and so on. This sequence can be expressed by the following rule. The n term is equal with 10 multiplied by n square plus 2. By doing these experiments, after few layers, we observe patterns of lines emerging. These patterns are defined by a combination of the underlining lattices of the faces of the cuboctahedron, and the periodicity of these planes. The cuboctahedron has two types of faces: 6 square faces and 8 triangular faces. The periodicity of the planes, in CPS geometry, has already been presented, early in this series. With these considerations, one finds that there is one common pattern emerging for all 6 sequences of square faces. The growing pattern, corresponding to the square faces, has a periodicity equal with 2. Every second plane, the pattern repeats and also adds new features. Another pattern is found to be common to the sequences of all 8 triangular faces of the cuboctahedron. The pattern, corresponding to the triangular faces, has a periodicity of 3 planes. From these observations, one can easily deduct that the periodicity of the CPS lines emanating from the central point of the cuboctahedron, has an overall growing periodicity of 6 layers. The pattern of lines, from each view shown here, are identical. The distance, between two neighbor points, is the same for all lines belonging to a view. The number of lines varies, and so does, of course, their spatial orientations. If you want to explore more these patterns, please visit our website, and play with the 3D patterns, available on the CPS Geometry viewer page. To get a deeper understanding of the CPS lines, we need to take the next step, and characterize the CPS lines by trying to compare them to one another by some kind of measurement. To do this, in the next few videos, we will introduce a metric relationship to characterize the distances between points in CPS geometry. Some very interesting surprises are waiting for us, just around the corner. Stay tuned. 2. The second way of investigating the patterns of lines in CPS is to use the fact that the rhombic dodecahedron is a space filler. If we look closer to the space, filled up with rhombic dodecahedrons, we observe that there are points where 6 rhombic dodecahedrons meet. Let's consider one of these points, and look at all the lines emanating from this point. Due to the fact that the distribution of the CPS points is identical for all 6 rhombic dodecahedrons, the fascicule of lines also has 6 identical components. These components have the same spatial orientation as the underlining rhombic dodecahedron. We can state, from this observation, that the CPS space itself has an underlining modular structure. If we choose one of the rhombic dodecahedron as the fundamental region, the distribution and structure of all the other regions can be obtained from here. This can be done by performing simple translations and rotations of the fundamental region. One might see here some analogy, or similarity, with the cross-ratios transformations, and with the rigid Mobius transformations, of complex analysis. The rigid Mobius transformations are unique types of Mobius transformations that map the sphere onto itself without stretching. They have been discovered by Gauss, and are associated with the elliptical functions. There are 2 ways to look at these rhombic dodecahedronal regions. 1. Each region can be seen as growing indefinitely. The vertex can be considered as the seed of the region. 2. Each region can be considered as being composed of smaller rhombic dodecahedrons regions, as already presented early in this series. Let's remember these observations for now. There is a lot more to be said about the patterns of lines in the CPS geometry. We will return to this topic later in this series.